Bismillahirrahmanirrahim. Assalamu alaikum dear students. Hope you're all fine. Today I'm going to deliver next lecture, chapter 13. Its name is Electromagnetism. Before delivering today's lecture, I want to review the previous chapter. It was chapter 12. In the previous chapter, dear students, we discussed in detail about steady current, Ohm's law, electrical resistance and resistivity, conductance and conductivity, thermistor, electromotive force, electric power, Kirchhoff's law, and Wheatstone bridge and potentiometer. After listening to today's lecture, you would be able to introduce electromagnetism. This is a branch of physics, magnetic field, and force on a current carrying conductor. First of all, we come to the definition of electromagnetism. Electromagnetism is basically a branch of physics. You can see here, it's a combination of that is electricity, magnetism. So electromagnetism means electric current and magnetism. When electric current passes through a material, then according to the effects of electric current, we observe magnetism. So it is a branch of physics that deals with the electromagnetic force coming from this magnetism that occurs between electrically charged particles. This is all according to our previous information. Magnetic recording media, VHS video home system tapes contain a reel of magnetic tape. The information that makes up the video and sound is encoded on the magnetic coating on the tape. Common audio cassettes also rely on magnetic tape. Similarly, in computers, floppy disks and hard disks record data on a thin magnetic coating. This is again for your information. Credit, debit and ATM cards. All of these cards have a magnetic strip on one side. This strip encodes the information to contact an individual's financial institution and connect their accounts. First of all, we come to magnetic field. It is just like an electric field. In the previous chapter, in electrostatics, we discussed in detail about electric field. Electric field, basically, it's a region around the charge. Similarly, magnetic field, basically it is a region. Electromagnetism, the region around a substance, a conductor, carries electric current. The magnetic field is the region around a magnet or a current-carrying wire in which it can attract or repel other magnetic materials. Students, in metric class, you would have learned about a simple magnet known as permanent magnet. Basically, a permanent magnet is a bar carrying two poles, North Pole and South Pole. The region around the magnet is known as a magnetic field. But dear students, in electromagnetism, we have to consider the magnetic field which is created by a current carrying wire, according to magnetic effect of an electric current. in which it can attract or repel other magnetic materials. This magnetic field, which is created by a current carrying wire, is the same as that of the magnetic field which is created by a bar magnet. We call this bar magnet as a permanent magnet, and this current carrying wire which creates a magnetic field is known as a temporary magnet, because its magnetism depends upon the current which passes through the wire. As current is passing, the wire shows magnetism. When there is no current, then magnetic field, it disappears. Magnetic field is a vector quantity and represented by a vector capital B, which is known as magnetic induction. With the discovery of electricity, it was soon realized that a steady current through a conducting wire creates a magnetic field around the wire. You can see here in the given figure, here is a current carrying wire, and the arrow, the blue arrow, shows the direction of flow of current through this wire, that is directed upward. And this is a region around the current carrying wire. Right? So the region all around the current carrying wire consists of magnetic field. A magnetic field basically consists of magnetic lines of force. Just in the same way as we observe that in case of electric field basically consists of electric lines of force. And these lines of force have a particular direction. Just in the same way, when we talk about magnetic field, which consists of magnetic lines of force, then these magnetic lines of force, they have some direction. And you can see the region around the current carrying wire, it consists of spheres, right? These are loops. So the loops may have two directions, maybe clockwise direction or maybe anti-clockwise direction. So it means magnetic field means magnetic lines of force can have directions clockwise or anti-clockwise. It depends upon the direction of electric current. The direction of such field is determined by right hand rule. Dear students, you are all familiar with the right hand rule. The stretched thumb and the curls of the finger, it shows direction. And here also, when we just grasp this current carrying wire in our right hand, then the stretched thumb indicates the direction of electric current, and the curls of the finger, it gives you the direction of magnetic lines of force. It may have clockwise direction, it may have anti-clockwise direction. So dear students, in the given direction, you can see that the direction of the current I is upward and the direction of the magnetic lines of force are, yes, anti-clockwise direction. Now, reverse the direction. If current is flowing in the downward direction, then the curls of the finger shows clockwise direction. You can perform this activity. Curl of the finger shows the direction of magnetic field, as I told you, while thumb indicates the direction of the electric current. The direction of the magnetic field can be verified by placing compasses on a card near a current carrying wire and observing their direction. Okay, you want to verify the presence of magnetic field. This could be done by introducing a magnetic compass. Dear students, you are all familiar with the use of magnetic compass. The presence of a magnetic field could be shown by the deflection of this magnetic compass. So what happens when we just when we bring this magnetic compass near a current carrying wire, then what happens? The magnetic compass, it deflects. So by changing the position of the magnetic compass, just place it at different points in the region around the current carrying wire, we observe a deflection. What does it mean? It shows the presence of magnetic. In the right hand rule, grabs the current carrying wire in your hand, curls the finger, stretch the thumb. The stretched thumb indicates the direction of the electric current, while the curls of the finger indicates the direction of the magnetic field. By reversing the direction of the electric current, that is, if thumb is indicating downward direction, then curls of the finger indicate the direction of the magnetic field, that is, clockwise direction. Current. Force on a current carrying conductor. When a current carrying wire is placed at right angles means perpendicularly to a uniform magnetic field, the magnetic field of the wire and external uniform field interact, resulting in a force F on the wire. So a magnetic force appears when there is an interaction of two magnetic fields. All right. The first magnetic field is created due to a current carrying wire. And what happens when we just place this current carrying wire in a region where there is already a uniform magnetic field? Then what would happen? The two fields interact with each other, and due to the interaction of these two magnetic fields, it results a force which is known as a magnetic force. Okay, so in order to understand the presence of this magnetic force, let me consider here an activity. For this purpose, let me take this magnet, which is known as a horseshoe magnet. It is placed, and here are two conducting wires. These are known as rails, and the terminals, the points of these two rails are connected with the terminals of the battery. So what happens when the two rails, conducting rails, are connected with the terminals of the battery? Then what happens? Electric current start to pass through them, and the green lines shows the presence of electric field, magnetic field. So as previously I told you, the magnetic effect of an electric current. So here there are two fields, one due to horseshoe magnet, the other field is created by the electric current which is passing through the conducting rails. And we notice that when the two fields interact, then what happens? What happens? It results a magnetic force. And you can see here in the activity that there is a rod. This is the rod, and it is capable of sliding over the two rails, and these two rails producing magnetic field, that magnetic field interacts with the magnetic field of this horseshoe magnet. So due to this, it results a magnetic force, and that magnetic force pulls this rod to move over these rails. All right. Let me say that the current which is passing through the rails is I. The magnetic force which is pushing the rod to move over these rails is F, and B is the magnetic field. So according to this activity, we can make a relationship between these three physical quantities. Which one? That is F, the magnetic force, is directly proportional to I and L. What does it mean? The magnetic force is directly proportional to I. What is I? I is the current which is passing through the conducting rails. Greater the strength of the electric current passing through the rail, the more would be the magnetic force. All right. And what is L? L is the length of the conducting rod. Greater the length, then more would be the force. So we can have a relationship between the three physical quantities, that is F, I and L. We say F is directly proportional to I into L. This is not a relation. In order to convert it into a relation, we add a constant, that is B. Here B is the strength of the uniform magnetic field. What is uniform magnetic field? There are two types of fields: uniform magnetic field and non-uniform magnetic field. In case of non-uniform magnetic field, the magnetic lines of force are not close, they are apart. In case of uniform magnetic field, the magnetic lines of force are close and parallel. Okay, this B in this equation is the strength of uniform magnetic field, which is called magnetic induction or magnetic flux density. And this magnetic flux density is the constant of proportionality in this equation. So we can find a relation between F, B and I with the help of a rule which is known as Fleming's left hand rule. You can see here this is a conducting rod and current I is passing through it, and these arrows shows the force and the blue arrow shows the magnetic field. This is a sign convention. The plus, this circle enclosing plus, it shows the magnetic field due to a current carrying conductor, not by a bar magnet. So you can find the direction of this magnetic force by using right hand rule, and in that case the curls of the finger indicates the direction of the magnetic field, the stretched thumb indicates the direction of the force, and this finger, it gives you, the middle one is giving you the direction of the electric current. If the wire is placed in the field B at some angle theta with it, then the force is given by the relation, that is F is equal to BIL sine of theta, where theta is the angle which the conducting rod, that is the Y, it makes with the field, that is F is equal to BIL sine of theta. Why we are using sine of theta here? Why we are not taking cos of theta? Because I told you earlier that here we have to place a conductor perpendicularly in a magnetic field. That's why we take here angle sine of theta. The vector form of equation number 1, F vector is equal to I, and inside the bracket we write down L cross B, where what is L? L is the length vector. Alright, because I told you that the length of the conductor carrying current I is a factor which could affect the magnitude of the strength of the magnetic force. That's why we call it as length vector. Cross B. So when this gives you another example of cross product of two vectors. Here two vectors are L and B, where what is L? L is the length vector, and what is B? B is the magnetic field. In the equation F is equal to BIL sine of theta, it shows that the magnitude of the force F on a current carrying wire of length L depends upon the following factors. So in the end, what we conclude that what are the factors on which the magnetic force depends? It depends upon how many factors? 4. Which one? B, I, L and angle theta. That is, B stands for magnitude of magnetic induction, I is the amount of current flowing in the wire, L is the length of the wire lying in the field, and what is theta? Theta is the angle between the two vectors L and B, means how the conductor is placed in a magnetic field, at which angle it is placed in a magnetic field. If it is placed perpendicularly, then the magnetic force would be maximum. Why? Because in that case theta would be 90, and we all know sine of 90 is 1. So the maximum force would be given by F is equal to BIL. If we keep B, I and L constant, then according to equation, force is maximum when theta is 90. Force is minimum when theta is 0, because sine of 0 is equal to 0. So that makes the magnetic force equal to 0. A force is a vector quantity, so its direction should be determined. The direction of F is determined by Fleming's left hand rule. Okay, in case of Fleming's left hand rule, we makes this gesture of your hand. The stretched thumb indicates the direction of the magnetic force. This finger, forefinger, indicates the direction of magnetic induction, and this finger indicates the direction of electric current. The SI unit for magnetic induction B is Tesla. TESLA is the unit of magnetic induction B, and it is abbreviated by capital T. And it can be defined as, okay, from the equation F is equal to BIL. When theta is 90, sine of 90 is 1. So we get F is equal to BIL, and from that equation eliminate for B. B would be equal to F over IL. Alright, so the unit of magnetic induction would be 1 Tesla when F, that is the magnetic force, is equal to 1 Newton, electric current I is equal to 1 ampere, and what is L? L is the length of the conductor carrying current I, that is given by 1 meter. So dear students, here we have got a very important relation which shows which gives you the definition of Tesla, that 1 Tesla is equal to it is equal to 1 Newton over 1 ampere into 1 meter. If the force experienced by 1 meter of a wire carrying 1 ampere current placed perpendicularly in magnetic field is 1 Newton, then the magnetic induction is 1 Tesla. Here is another unit of magnetic induction which is known as cos, and cos is indicated by capital G, and the relation between cos and Tesla is given by 1 cos is equal to 10 raised to the power minus 4 Tesla, or 1 Tesla is equal to 10 raised to the power 4 cos. So in this way, if you want to convert cos into Tesla, you can use this relation, and Tesla into cos, you can use this relation. These are the basic equation for the conversions. Here is a solved example, that is the first solved example of the chapter. 13.1. A wire carrying 2 ampere current and has length 10 centimeter between the poles of a magnet is kept at an angle of 30 degrees to the uniform magnetic field of 0.6 Tesla. Find the force acting on the wire. First of all, we come to the data given. In the data given, what is 2 ampere? Yes, this is I current. And what is this 10 centimeter? Yes, L, this is the length of the conductor, 10 centimeter. Definitely we have to convert it into meter. For this purpose you will divide it by 100, that gives you 0.1 meters, and B is equal to 0.6 Tesla. And what is theta? At which angle it is placed in a magnetic field? Theta is equal to 30 degrees. And what is required? F. F we have to find. We come to the solution. The formula we are going to use here, F is equal to BIL sine of theta. Putting all the values here in this equation, what we get, F is equal to 0.06